Why is this damn space so huge? Of course, on the one hand, that's also a part of why we like it. But on the other hand, for us, space enthusiasts, those who want to learn as much about space as possible, it creates a lot of problems. Huge distances make exploration of even our own solar system extremely difficult, not to mention interstellar travel. And for many of us, interstellar journeys, worlds around other stars, are a dream. At the same time, many people, including specialists, believe that we will never leave our solar system. Too many problems arise with interstellar travel, many of which cannot be solved, at least with the methods available today. And then, suddenly, almost out of nowhere, in 2016, the Breakthrough Starshot project appears. Within it, the possibility of launching interstellar probes in the coming decades is being discussed. Of course, this is not what we are used to in science fiction, but still, the possibility of studying an exoplanet, an Earth-like exoplanet in the habitable zone, possibly even seeing images of it. It is not surprising how many people were excited by such a project, however bold the plan might be. Of course, the project also had its critics, but it still made a lot of noise. Because first of all, it was supported by a large number of prominent scientists, among whom were Stephen Hawking, Freeman Dyson, Martin Rees, and many others. And secondly, it was said that billionaire Yuri Milner would donate as much as $100 million to the project. After all, many ambitious projects collapse in their early stages precisely due to lack of funding. I've mentioned the Breakthrough Starshot project many times in my videos, including in the context that this project, or something similar to it, might be our best chance, at least in some form, to launch a real interstellar mission that could reach its destination in a reasonable time, rather than in thousands or tens of thousands of years. And yet, for quite a while, there haven't been any significant updates from the project. And recently I was browsing space news, as I usually do, and I come across a news article about a study describing another similar project, which proposes launching multiple microprobes to Proxima Centauri, not connected to the Breakthrough initiatives. The article, of course, also mentions the Breakthrough Starshot project, but says that it is already defunct? And I'm like, wait a second. I usually follow space news pretty closely, and I don't remember seeing any official announcements that the project was shut down. Did I somehow miss it? But no, there were no official announcements about the project being closed. The website is still active, and even some relatively recent minor updates can be found on it. And yet, a number of scientists and engineers who were directly involved in the project say that the project is likely over. And in general, not everything about it was as rosy as we thought. There was also a fairly detailed article about this, published not long ago in Scientific American. Let's try to figure out what is happening with once promising interstellar project Breakthrough Starshot. Talk about the plan itself, the technologies, the problems, and what in the end might have doomed this famous project. I'm Andrei, and this is Cosmos Elementary. I've talked about interstellar travel many times before and discussed different aspects of this topic, both the various problems and how they could be solved, at least in theory. We are well aware that the main problem is the enormous distances. Everything else follows from that. If we take modern propulsion systems that are already available and actively used, chemical rockets or electric ones like ion engines, the journey even to the nearest star to the Sun would take tens of thousands of years. And yet, even with the conventional engines, we have already launched spacecraft that could one day be called interstellar. 5 of them, in fact. Pioneer 10, Pioneer 11, Voyager 1 and Voyager 2, and the New Horizons spacecraft. They are all still under the influence of the Sun's gravity, so it cannot really be said that they have fully left the solar system. However, their trajectories are such that one day they will eventually leave it completely. They are not flying toward the nearest stars. They may have once come close to some planetary system or even a planet, but that could happen only in hundreds of thousands or even millions of years. And already now, 2 of these spacecraft, the Pioneers, are no longer functioning. Contact with them has long been lost, and they are flying through space like ghost probes. With the Voyagers and even more so with the New Horizons spacecraft, communication is still maintained, but they will also lose power long before they even leave the solar system. Here we can perhaps console ourselves with the idea that, in a sense, we have still launched something toward other stars, even if these are only dead interstellar artifacts. Even if our civilization were to disappear entirely tomorrow, something of us would still remain in space, and one could even imagine that one day someone might come across these spacecraft far beyond the solar system. They might learn something about us from them. Only we would no longer be there, perhaps not even as a species. Yes, in theory, even chemical rockets can accelerate for a long time and reach enormous speeds. But they require so much fuel that the whole idea becomes pointless. In short, with modern methods, we can technically launch a spacecraft that one day will become interstellar, but we will not live to see it reach anything, and it will not be able to send us any information back. Right now, new methods of acceleration in space are being developed that could allow much higher speeds with lower fuel consumption. For example, various types of nuclear propulsion. In most cases, they could reduce the travel time, say, by a few times, but it would still take an extremely long time. But a nuclear pulse engine, for example, stands somewhat apart here. In this type of propulsion, in which nuclear charges are released behind the spacecraft to propel it forward, in theory it could achieve a significant fraction of the speed of light and reduce the travel time to the nearest stars to decades. But this is a quite extreme method, and for now it is also not very realistic, although it is theoretically possible. Of course, we could ignore speed and travel slowly, even with humans, on something like a generation ship. However, people remaining on Earth would not learn the results of the journey for a very long time. And such a mission also has a huge number of problems, starting with the standard issues of space radiation, long-term life in a closed environment, resupply of resources during the flight, and so on. If we still consider at least somewhat realistic ways of accelerating to a significant fraction of the speed of light in order to avoid extremely long travel times, the problems related to speed begin to appear. And I'm not even talking about how to reach it, but also about the fact that at such speeds, even a tiny dust particle can cause significant damage to the spacecraft. And about the need to slow down as well, and if you don't slow down, then you have to manage to measure and observe something while passing by at enormous speed, and so on. As for truly science fiction-like technologies like warp drives, we're not even discussing them. Although something like that may be theoretically possible, we will most likely not be able to create anything of this sort for hundreds or even thousands of years if we ever manage to create it at all. And still, the idea of interstellar travel continues to fascinate scientists and engineers, and they keep exploring individual aspects of it. Research papers are being published about it, and various experiments are being conducted. Still, from time to time, organized research projects do emerge, and besides Breakthrough Starshot, there have been others as well. For example, the 100-Year Starship project. This is a joint initiative by NASA and DARPA, whose main goal is to assess what would be required to send humans to another star within the next 100 years. In this case, some funding was allocated for research, for example a $500,000 grant. Regular conferences were also held. The Tau Zero project, a private non-profit organization that supported research in the field of interstellar travel through private donations. And within this project there was, for example, the project Icarus. It involved theoretical research into the creation of a thermonuclear propulsion system for an uncrewed interstellar spacecraft that could reach 10–20% of the speed of light. This is very brief, and I might still make a separate video about some of these projects and the research conducted within them. Still, compared to those examples, Breakthrough Starshot is much better known. It also had a much more high-profile announcement and significantly larger funding. Although we will talk about that in more detail later, since even there things are not entirely clear. And probably the Breakthrough Starshot plan was also the most ambitious. The timelines although not exact, but at least approximate ones that were sometimes mentioned, were clearly more optimistic than in other cases. And the optimism was based precisely on the approach chosen within the project. The main goal of the Breakthrough Starshot project is defined as demonstrating the fundamental feasibility of launching and accelerating ultra-fast interstellar nanospacecraft driven by light. In the previous part of the video, I mentioned some major problems of interstellar travel, and this approach, in theory, could solve many of them. The use of nanospacecraft, more precisely gram-scale spacecraft, meaning each one should weigh no more than a few grams, addresses the mass problem. The lighter the spacecraft, the easier it should be in principle to accelerate it. For acceleration, a light sail would be used. We've discussed space sails in general and the use of light for acceleration in space many times before. Although photons have no mass, they carry energy and momentum, which means they can propel a spacecraft. And this is not just a theory. It has been repeatedly proven experimentally, and working prototypes with light sails have even been launched into space, demonstrating their feasibility. The challenge of using sails to accelerate a conventional spacecraft with a mass of hundreds of kilograms, and especially a large crewed vessel, is that the sail must have an enormous surface area while remaining extremely thin. Secondly, if a sail is used for acceleration using sunlight, the effectiveness of such acceleration quickly decreases as the spacecraft moves farther away from the sun. In the Breakthrough Starshot concept, the problem of sail size is solved by the very small mass of each individual probe. According to calculations, it would require a sail only of about 4 to 5 meters across. And instead of the sun, powerful ground-based lasers are proposed for acceleration. With sufficient laser power, a single spacecraft could accelerate for only about 10 minutes, and during that time reach 20% of the speed of light. However, the problem of the space environment during flight still remains. Collisions with dust particles and everything else, protection is also being discussed. But another proposed solution is to launch not one, but 1,000 of these nanospacecraft. If some of them are destroyed during the journey or become inoperable, there is hope that at least a fraction of them will reach Proxima Centauri. In this scenario, a mothership is launched into Earth orbit. It releases nanoprobes, which are then accelerated by Earth-based laser to 20% of speed of light, allowing them to reach Proxima Centauri in about 20 years. If by that time some of the probes are still functioning and do not miss the planet, at least coming close enough, they could collect data, possibly take images, and transmit the information back to Earth. We would then begin receiving those signals about 4 years later, plus a little over that. It doesn't really seem like anything purely fantastical. We can build microelectronics, we've tested light sails, we know how to build lasers. Each component of the mission already exists in some form. The other question is whether it exists in exactly the form needed for a successful mission like this. And yes, in practice there are many nuances at every stage, and we will talk about them as well. But the general idea is this. On the official Breakthrough Starshot website, there is a section called Research. If we go into it, we can see a large list of scientific studies from different years on interstellar travel, covering many different aspects of the topic. And within this list, the first article is Philip Lubin's paper titled A Roadmap to Interstellar Flight. And it is not listed first by coincidence. Apparently, it is one of the main reasons why the Breakthrough Starshot project itself came into existence. And if we browse through this paper, even just quickly scanning the table of contents, we can see all the core components of Breakthrough Starshot outlined there. A small spacecraft, laser acceleration, and everything else. The only thing is that the project itself has not been mentioned yet. In the Scientific American article I mentioned, it is written that former director of one of the NASA's key laboratories, the Ames Research Center, Pete Worden, showed Lubin's work to Yuri Milner. And Milner, according to this article, saw in it essentially a ready-made plan. And soon after, that very press conference took place. where Yuri Miller announced the creation of Breakthrough Starshot project and the allocation of $100 million to it. And Pete Worden became the head of the project. Originally, the announcement was about a mission to the Alpha Centauri system. However, later in 2016, the discovery of Proxima Centauri b was announced, a potentially Earth-like planet even located in the habitable zone of its star, the closest star to the Sun. And later, this newly discovered planet became the main target. The story also caused quite a stir because such a large sum became one of the biggest private donations to fundamental science. I recently made a video about who should pay for space exploration and for fundamental science in general. And there were very few examples of large-scale private funding of fundamental science, and Breakthrough Starshot was one of the very few such cases. And in the field of interstellar travel, there has never really been anything like that at all. But as it turned out, even here things are not quite as we thought. When you hear a short description of the Breakthrough Starshot project idea, it seems to me that you don't even need to be an engineer or a scientist with many years of experience to notice a number of problems in this concept. Of course, this was also understood by specialists, and none of these problems were ignored. The project website has a whole section listing the problems that need to be solved in order for an interstellar launch like this to become possible. It includes a brief description of the problems, the current state of the field, and links to relevant research on each of these topics. The problems essentially exist for every key component of the mission. We can't say that any of them are fundamentally unsolvable, but some are very serious. We're used to satellites being fairly large. They can be, say, the size of a car and have a mass of hundreds of kilograms or even several tons. The Hubble, for example, has a mass of over 11 tons. In recent years, CubeSats have started to be actively used. Small satellites with a side length of around 10 centimeters, or about 4 inches. Or roughly 1/1000th of a football field. But for Breakthrough Starshot, the spacecraft need to be even smaller. As I already said, it has to have a mass of just a few grams. At the same time, it has to contain a minimal set of components to carry out its tasks. The brains in the form of a tiny computer and instruments for collecting data such as a camera and communication device, and ideally some kind of micro thrusters for minimal maneuvering, and energy source to power all of this. Is it possible to fit all of this onto a platform just a couple of centimeters in size? Well, in general, electronics can already be extremely compact. Each of you has a smartphone that, in terms of computing power, far surpasses the computers, which used to occupy entire rooms. Plus, they also have a lot of other functionality, take cameras for example, which can also be made quite compact. But have there already been attempts to build such microsatellites? And is there a specific prototype within Breakthrough Starshot itself? A few years before the project appeared, in 2009, aerospace engineer Zachary Manchester began developing spacecraft the size of a postage stamp. He called them CubeSats, or sprites. Through crowdfunding, it raised money for the first launch, which took place in 2014, but it turned out to be unsuccessful. But in 2019, there was an attempt to launch a second version, and it was successful. In this case, again, a small mothership was launched first, and it deployed 105 CubeSats. They operated as a single swarm and demonstrated that they could communicate with each other and transmit signals. However, after that, such launches were banned. Now the problem of space debris is becoming increasingly serious. The danger is not only that a single large satellite may collide with another one, but also that such a collision would generate a huge amount of small fragments, which would also travel at extremely high speeds, and each of these fragments can cause significant damage to other satellites or even to the ISS. And here we are launching 100 small objects right away. But if such launches are carried out farther away from Earth, that problem would no longer exist. And it is precisely Manchester's CubeSats that became a kind of prototype for the nano spacecraft of Breakthrough Starshot. And Zach Manchester himself joined the project team. And yet, even so, these CubeSats are still very far away from becoming real interstellar spacecraft. They would need every component replaced, in most cases, with fundamentally different ones. Probably one of the least problematic components of such an interstellar spacecraft is its logic or computational system. Today, microprocessors weighing as little as 1 gram already exist. Yes, specialized chips would need to be developed specifically for the mission's requirements, but there is nothing fundamentally impossible about that with today's technology. In the case of cameras, things already become significantly more problematic. And not so much because we are incapable of building a camera small and light enough for the whole nanospacecraft to fit within a few grams. We can make cameras. At the very beginning, you can ask a question: do we even need a camera there? For many people, such a question will seem strange. Why send a spacecraft to another planetary system at all if we won't be able to see anything? But here, this is intertwined with another key component of the mission: communication. We can't really talk about recording 4K video with an individual probe and transmitting all of that back to Earth with something that small, of course. Therefore, some of the people involved in the project even suggested that instead of images, it would be much easier to transmit just a short message. For example, an answer to a question in a yes-no format. Let's assume the instruments on the spacecraft obtain information about certain properties of the planet, such as its atmosphere. We predefine a question in advance, for example, is there oxygen in the atmosphere? And the probe would only need to send us a single bit of information to answer. Either a 1 or a 0, yes or no. That may sound more realistic, but at the same time, it is far less appealing than the possibility of directly seeing a planet in another system. That is why the project ultimately did not abandon cameras. On the website, in the challenges section, it says that cheap 2-megapixel cameras are already available today with a mass of less than 1 gram. This website section was filled in some time ago, so even better cameras are available now. But the problem is that ordinary cameras, like the ones in our smartphones, might not be well suited for the conditions that an interstellar nanospacecraft will face. If it does manage to reach Proxima Centauri and get close enough to the planet Proxima Centauri b to actually take any meaningful photographs. If the spacecraft is moving at 20% of the speed of light, it is roughly 60,000 kilometers per second, not per hour, per second. In other words, more than 200 million kilometers or 124 million miles per hour. Let's assume we get a spacecraft where we want it to go to, and it passes very close to the planet. How much time will it have for observations? I made a visualization like this in Space Engine of a flyby past Earth at 20% of the speed of light. In the presentation animation of the project, a similar kind of flyby is shown, and in that case we would only have a few seconds for imaging at closest approach. Everything has to be fully autonomous, because the signal delay to Earth is 4 years, after the spacecraft has already traveled for 20 years. Assuming all key onboard systems survive the journey, a conventional camera would still need to point, adjust its orientation and focus. Relying on that doesn't feel very appealing. So ideally, you'd want to avoid the need for focusing altogether. And such a solution does exist. PFCA cameras. PFCA stands for Planar Fourier Capture Array. These are systems with light-sensitive sensors, but without lenses, mirrors, or any moving parts. The sensors of such a system collect data, but the final image is then reconstructed from the data using computational methods. Such a camera does not need to be focused and can be much more compact than a conventional camera. Of course, the image from such a camera would not be as detailed as from a traditional one. But still, assuming the spacecraft gets sufficiently close to the planet, we would be able to discern some surface details. At that point in the project descriptions, it is often stated that ideally, the spacecraft should get as close as about 1 astronomical unit to the planet. That is 150 million kilometers, or about 93 million miles, or the distance from Earth to the Sun. So what would the spacecraft be able to see in that case? I found a visualization showing what Earth would look like during a flyby by a Breakthrough Starshot probe moving at 20% of the speed of light at a distance of just under 3 astronomical units, under 1.5 AU and 0.12 AU. The planet no longer looks like just a point, and some surface details can already be seen from a fairly large distance. But I have some doubts about this. Here, there is no description of camera parameters, and I'm not sure that this level of detail can be achieved with a lensless camera without optical magnification. So in short, it is better to get as close as possible. And you've probably also wondered, how would the spacecraft even get that close to a planet in the first place? Even within the solar system, sending a spacecraft to another planet is not a simple task. It requires observations of the target's planet to determine its orbit and motion with high precision. A lot of calculations are needed, and in the solar system, we can see planets and other objects directly. By the way, I made a detailed video about how orbital calculations are done and how we predict where a given solar system object will be in the future. So Proxima Centauri b is not observed directly. The planet was detected using indirect methods, specifically the Doppler spectroscopy method or the radial velocity method. Not only does the star affect the planet through its gravity, but the planet also affects the star, causing it to wobble slightly. Because of this wobble, from a certain observing angle, the star will periodically appear to move slightly away from us and then closer to us. As a result, its spectrum shifts alternately towards the red and the blue part of the spectrum. And based on the patterns of these shifts and wobbles, we can determine the presence of a planet and some of its properties, such as its period and its distance from the star. In any case, the proposal is to collect as many observations as possible before launch, using the largest available observatories, as well as space missions like the Gaia spacecraft, which has completed its mission and was measuring the position and motion of stars in our galaxy. So even without the ability to observe directly, we can still obtain a certain understanding of an exoplanet's orbit and of where it is located at a given moment, and refine these estimates as new data becomes available. In any case, this is not about necessarily getting within a couple thousand kilometers of the planet's surface. The margin is quite large, about 150 million kilometers. And again, the idea of sending not one nanospacecraft but 1,000 of them can help here. If there is some uncertainty in the planet's orbital position, we can send multiple spacecraft to slightly different regions of the system. Some would be placed within certain limits on the one side of the star and others on the opposite side. And then we hope that at least some of them will turn out to be close enough to the planet to take a picture of it. But still, it is preferable to refine the planet's orbit as accurately as possible. Here, there may also be hope in next-generation telescopes that could be capable of directly imaging Earth-like planets around nearby stars. But let's assume the spacecraft actually arrives at the right place and gets close enough to the planet. What happens next? Let's say a planet is right here, very close, but the spacecraft is oriented like this. And that's it. We won't see anything. In short, the spacecraft also needs some kind of active altitude and orientation control system, both for pointing the camera at the target and then for pointing back toward Earth to transmit a signal. It's hard to imagine how a spacecraft of such a small size could carry an altitude and orientation control system comparable to those used on large spacecraft and space probes. Here, instead of conventional thrusters, the idea is to use tiny photon thrusters. It sounds like science fiction, but in practice, it is just small LEDs or laser diodes. I already mentioned today that light carries momentum, which is what makes solar sails possible in the first place. But this also works without a sail. If we are in space, far away from massive bodies, place a flashlight and turn it on. Because it emits photons in one direction, it will begin to very slowly accelerate in the opposite direction. Like in conventional rocket engines, except here instead of gas we have photons. So if several such emitters are placed on the spacecraft and they are activated in a controlled way, it creates an asymmetry, and the nano spacecraft begins to rotate. As an alternative to visible light, you can also use thermal radiation from the power source, again creating an asymmetry. Speaking of the power source, this point is listed on the official website as one of the main challenges of the mission. Spacecraft usually use two main types of power sources. First of all, solar panels. Second, in cases where the spacecraft travels too far from the sun, or there is a risk that solar panels may become inefficient over time due to dust, as is in the case with some Mars missions, RTGs are used instead, radioisotope thermoelectric generators. The radioactive material in them, for example plutonium-238 oxide, gradually decays, releasing energy in the process. In simple terms, this produces heat. A thermocouple made of two different conductive metals or alloys generates electricity when heated. That's the very short version. Manchester's chipsets had miniature solar panels, but for our interstellar spacecraft, this is not the best option. Although there was an idea to cover the spacecraft's sail with photovoltaic elements, effectively turning it into a solar panel. As the main option for Starshot, something like a miniature RTG was considered. The goal would be to make such a device with a mass of no more than 150 milligrams. All of this is still very far from being realized, which is why power supply is considered one of the main problems. As I said, without power, nothing will work. And no one is going anywhere without a suitable sail. The sails that have already been built were made from polymers, and that would not work in this case. We need a sail with a diameter of 4 to 5 meters while keeping the mass below 1 gram. Plus, it must not melt under a powerful laser beam, which means it needs to have almost perfect reflectivity. Furthermore, it must withstand immense acceleration. Remember I said that the laser acceleration would last for 10 minutes, and during this time the craft must reach 20% of the speed of light? The g-forces involved could be approximately 40,000 Gs. The sail must withstand such a load, as, by the way, must all the other equipment and the spacecraft itself. The hope lies in new, perspective, ultra-strong materials. Studies have been carried out using silicon nitride. It was possible to create samples thinner than a micron. It was assumed that the sail would be assembled from separate pieces like a jigsaw puzzle. So far, only millimeter scale samples have been achieved, whereas meters are needed. Overall, there has been some progress here, but for what would be required in the final mission, it is still very far away. Another issue that, according to some project participants, has not received enough attention is communication. I already said that due to communication difficulties, some even suggested abandoning images altogether and limiting it to short messages. But still, in theory, how could such a tiny spacecraft transmit a signal to Earth? For pointing toward Earth, a star tracker would also be useful, which determines the correct direction by using the stars. For transmitting a signal, a laser on board the spacecraft could be used. But how could you see such a tiny laser from a distance of 4 light years? It was proposed to use the spacecraft's 4-meter sail as an antenna or as a device for focusing the signal. The idea was that before sending a signal, the sail could be shaped into a Fresnel lens configuration and used to focus a weak laser signal in a specific way. And to detect a still very weak signal on Earth, extremely powerful instruments would be still required. An interferometer at least on a kilometer scale, and ideally not even on the ground but in space. We have never built such large structures in space yet. All of this, the lasers, photon engines, power systems, cameras and sail, has to survive the journey intact. It must not be destroyed during acceleration, not degrade over a 20-year cruise at 20% of the speed of light, not be damaged by interstellar dust, and not fail due to cosmic radiation. But that's not all. First, many of the issues I listed here have their own sub-problems, and overall the full list of challenges is actually longer. However, the main problem many people point to is not even in space, but on Earth. Lasers. To achieve this kind of acceleration, even for such a small spacecraft, you would need a system on the order of 100 gigawatts. And building a single laser of that power is something we cannot currently do. That is why a phased laser array is being considered instead. Many weaker lasers, synchronized in phase, can together function as a single coherent beam. Using a phased array also allows you to steer the beam and aim it at a target without any physical movement by simply changing the phase of the beams or adjusting the delay between individual beams. Again, this sounds like something we could do in theory, and at smaller scale such arrays have already been built in laboratories. But at the scales and in the configuration required for launching an interstellar probe, a whole bunch of problems arise. The laser beams from the ground pass through the turbulent atmosphere. And since the beam is made of multiple individual beams, this can cause them to become desynchronized, which in turn could destabilize the spacecraft. This can be mitigated with an adaptive optics system, which is already widely used in large telescopes. When a laser beam is sent into the atmosphere, it creates an artificial star and is used to measure atmospheric fluctuations. And the mirror literally slightly deformed in real time to compensate for distortions caused by the atmosphere. In the case of a laser array, it is also possible to use a separate pilot laser beam, but here the problem is that the scale is larger than in telescopes. This means that corrections would have to be applied an enormous number of times per second so that the beam does not end up spreading out. In addition, we will be significantly heating the atmosphere locally by firing such a powerful laser through it. It would also be important to ensure that this laser does not accidentally ignite or damage anything either in the atmosphere or in space. But the biggest problem is probably where to get that much energy from. 100 gigawatts? An average nuclear reactor produces about 1 gigawatt. Does that mean we need about 100 nuclear power plants for a single system? In today's reality, this is practically impossible to imagine. It would cost billions and billions, if not trillions of dollars. So we are left hoping for some kind of technological breakthrough in energy, and Pete Worden wrote that lasers and their power supply are the main technological challenge of the project. But as it turned out, what may have killed the project was not even that. Of course, the $100 million mentioned in every press release would not have been enough to complete the project as a whole. For that kind of money, you can barely launch a mission to Mars using only proven technologies. As we have already established, there are problems with every key component there. The infrastructure for launching it would cost an absolutely enormous amount of money. $100 million is more of a budget for the core research. The only problem is that apparently even that $100 million never fully materialized. The authors of the Scientific American article I mentioned contacted the project leaders for comments, including Pete Worden. Two of them declined the interview, but Worden still provided some comments in an email. The comment was given also by Philip Lubin, the author of the very article that inspired Milner to launch the project and to allocate such a large sum of funding, and which also formed the basis of the project itself. Lubin said that in the end, no $100 million were actually allocated. The project expenditures were not disclosed. For example, Lubin's group received two grants, $116,000 and $80,000 over roughly 8 years. It is known that a group from Australia received $80,000. Some groups carried out research within the project without funding from the breakthrough initiatives. Most of the groups met regularly at conferences and communicated with each other. Lubin roughly estimated that over 10 years, about $4.5 million were likely spent on 30 contracts. This figure is not exact, but it is an estimate from a project participant. In any case, it seems to be very far from the claimed $100 million. There have been no announcements of any progress for a long time. In fact, practically nothing has been heard at all. There has been no official statement about the program being shut down, but Pete Worden, the executive director, replied in the email. The program is on hold while portions of the project are transitioned to others. So, at least at first glance, it seems that the project has been put on hold indefinitely, which likely means its end. Similar comments have also been made by other participants of the project. It is possible that as the issue was studied more deeply and a better understanding of the problems still to be solved emerged, it became clear that the results are still very far away, possibly 50 years or more. And they didn't want to spend $100 million on something whose results they might not even live to see. This is also related to the question of who should fund science. In this case, a large project involving many research groups depended on the funding of a single individual. If that person suddenly loses interest in the project or for some other reason stops providing funding, the project comes to a halt. Fundamental research often requires large investments, a lot of time and patience, and it does not always lead to practical results or even to the results that were originally expected. Today, a billionaire may be interested in a project of interstellar probes, and tomorrow he may lose interest. And that's it. The project is over. Still, within the framework of the project, some progress has already been made, both theoretical and experimental. There's now a better understanding of what is required to accomplish such a task. Some research on this topic continues to be published, even when it is no longer directly connected to the project of Breakthrough Starshot. This is actually how I came across the story about the current situation. In general, it cannot be said that all of this was in vain. And although today we saw how serious the problems are with the individual components of the mission, there still doesn't seem to be anything fundamentally unsolvable here. With sufficient resources, time and persistent step-by-step work, it could one day be achievable. But it seems that unless something changes drastically within the framework of the Breakthrough Starshot project itself, no interstellar probes to Proxima Centauri b will be launched. Too bad.